Hello, everyone. My name is Fernando. I'm going to talk about unique decoding explicit epsilon balance codes near the Gilbert Varshamov bound. This is joint work with Quintana, Shashank Srivastava, and Madhur Tulsiani. And the plan of the talk is our goal is going to be to present a new unique decoding algorithm for a family of binary codes due to attachment. And we are going to explain those shortly. Roughly, that's going to be our goal. And the outline is going to be as follows. So you're going to spend 1/4 of our time talking about notation and context. I think that the history here is quite interesting. And we are going to talk about direct sum, which is it's an important component in Tashma's codes. Okay. And the second half of the talk, we're going to discuss our decoding techniques and give a flavor. So I would like everybody to at least have a clear idea of the results, and potentially foreign specialists of coding theory to have a flavor of the techniques. That's going to be my goal. And a binary code is the simplest object that you can imagine, right? So it's just a subset of strings. So you have this space f2 to the n, and the code words are those black boxes. And you have two fundamental parameters: the distance, which is the minimum over pairs of distinct code words, of the normalized, and we're going to work with the normalized Hamming distance. This is a key parameter of the code. And the second one is the rate, which is a fraction of information symbol. So you take the size of the code, you take the log, you divide by n. This is giving you the fraction of information symbol, and we call this RC. Okay, so you have distance, you have rate, fairly fundamental. Now we need to define the error model, right? And the error model is going to be an adversarial error model. So Alice wants to send a code word to Bob. There is this noise channel. There is an adversary here that can flip bits arbitrarily. It has unbound memory, unbound computational power. The only restriction is that it can only change at most a p fraction of symbols, but in any way that the adversary wants. And how large can we take p? This is a well-known fact. Information theoretically is going to be at most roughly half of the minimum distance. Because if you corrupt about half here and about half here, and potentially you flip here, you don't know which ball you came from, which code word you came from. So you need to stay within those balls, and those are the unique decoding balls. Very good. This error regime was introduced in seminal work by Hamming in the 1950s. And we have this tension. So you have the rate, how many code words you're packing, and you have the distance. If you pack more, they might be closer to each other. And if you require a larger distance, we might not pack as many code words. So in picture, this is a low rate code. You can have larger distance. And if you try to pack too many code words, they might end up having a smaller distance. So putting those two together, you see that there is a tension between the two. And the natural question is, what is the best trade-off that we can achieve, right? And somewhat soon after Hamming proposed his adversarial model, Gilbert came up with an existential result. It's non-constructive. He said that for any fractional radius that you want, there exists a code that's reasonably large. So its size is 2 to the n divided by the volume of a ball of radius whole. And in terms of rate, this is roughly equivalent to 1 minus the binary entropy of whole. And the idea was fairly simple. He realized that, oh, I can do this greedily. So for each word that I would like to declare as a code word, I'm going to take with it all the words within this ball. And if you do this, we know that every other subsequent code word will satisfy the minimum distance. And you repeat this process. So you take a point, you carve this ball, and then you repeat. And this is a very simple greedy procedure. But you're doing this procedure in an exponentially large space, so it's not constructive. And why do we care about this Gilbert simple bound, this Gilbert Varshamov bound? Is that it's nearly optional, and nearly, of course, depends on the eye of the beholder. But for us in this talk, we are going to declare the G bound to be nearly optional. And the reason is this: you have this curve. It's giving everything below here is we have. There are codes for this. They may not be explicit. But a little bit above, we have some impossibility results. You cannot do much better than the Gilbert Varshamov bound. And in this talk, you're going to be interested in this regime, right? You're going to be interested in distance half minus epsilon. Okay, very good. And more concretely, what the GV bound tells us? It tells us that rate epsilon squared is possible, and you cannot do much better. So for instance, the best that you could do potentially would be an extra log 1 over epsilon factor. So in this sense, the GV bound is near optimal for us. Okay, and it took a lot of years for an explicit construction to emerge, right? Tashma had this breakthrough result of codes of this distance. Actually, they were a little bit stronger. They satisfied not only that the Hamming weight of the difference of code word was bounded below, but also above by half plus epsilon divided by 2. And the rate here is near optimal, and you see that this factor is this little of 1 is going to 0 as epsilon goes to 0. Fairly good, but one question was open. Now we have this nice code near the Gilbert-Varshamov bound. It's explicit, but can we decode it efficiently? That was the main question left open. And in this work, our main result is yes. Tashma's codes, they admit efficient decoding. And if you want to inspect the parameters, our main result is as follows. We have Tashma's codes. The little OA hertz is this. It's slightly worse than Tashma's, but close. And the running time is polynomial, right? So this is the block length, and here have an exponent that we are hiding factors of epsilon and beta. And if you're curious, those are polynomial factors. And if you're willing to trade the quality of this beta, if you want to take it to be an arbitrarily small, but you fix it, then what you're going to see is a running time that no longer depends on epsilon, on the exponent. So at least with respect to epsilon, it's fixed polynomial time. Okay, and we do a little bit more. We can do least decoding. This doubles the unique decoding ratios, but the parameter trade-offs are not great. The distance versus rate is good, but the least decoding ratios is nowhere near the state of the art. And in terms of previous results, there are efficient decoders for non-explicit codes near the GV bound, even near linear time. And in terms of least decoding, the best that is known is this trade-off. You have distance half minus epsilon and rate epsilon cubed. Okay. And now let's move towards Tashma's codes, and those are going to be based on this interaction of expanders and codes. And you're going to start with a base code of potential small distance, and you're going to use the pseudo-random properties of the expander to boost this distance. Let's explore this in a concrete setting. So you have this bipartite graph between N and double K, which is a collection of tuples. And this is the bipartite graph. It has any vertices here, and here's the collection of tuples. Let's take a code word here, right? And then you identify each symbol of this code word with a vertex in our bipartite graph. And then for each vertex here, you're going to look at the neighbors that we have, and you're going to collect. So the tuples they are indicating the neighborhood of this guy, and you're going to take the XOR of the corresponding symbols attached to the neighbors. And if you think, you start with a code of block length n, and you're ending up with a code of block length double size of double k, right? So we have this kind of loss, right? And we want to do distance amplification. You need to see the trade-off between the two, right? You're amplifying the distance, but you're also losing the rate. And the trade-off between the two is going to be crucial here. Okay, so this kind of amplification for direct product for different encoding those due to those alters. It's not and what is the direct sum? So the direct sum is you start from any word in the base space, and then you have any collection, and then what you're going to do, you're going to form a new code word in this larger space, such that it's going to take the XOR of the symbols corresponding to the positions of the tuple. And you're going to denote this by this sum. the sum using this collection at this base code, this base word is going to give us this y. Very good. And an important quantity here is going to be the bias. And the bias is just the difference between the zeros and ones. And they are going to work with this normalized version. And the bias of a code is just the worst bias that you see for non-zero code words. And Tashma used this very nice definition to understand when a collection of tuples reduce the bias. So you're going to say that's an epsilon zero and epsilon paired sampler. If you're starting from any word, it takes bias epsilon zero all the way down to a potential much smaller bias epsilon. This is a paired sampler. And where are they, right? I would like to construct those guys, and where are they? And one naive way of constructing them, take all the all tuples of length k. And here the decrease in the bias is amazing. It's the exponential in k. But you're paying a lot, right? This is shoe dense, and for coding theory purpose, it may not be ideal, right? You have codes of vanishing rate. You could alternatively not be too greedy, sample just a small, sparse collection of this size. And then it's not hard to show that it's going to be a very good paired sampler, achieving near optimal parameters. But the problem is that it's non-explicit. You're using a lot of randomness there. Okay. So one solution was, if you want tuples, a collection of tuples of size k that's reasonably sparse, take a sparse expander and consider all walks of length k minus 1. This is quite good, but not optimal. It achieves distance half minus epsilon and rate about epsilon to the 4. And it was proposed by Roseman with Derson and analyzed later by Tashma. And now, what is the nearly optimal construction? So instead of taking all walks of length k minus 1, Tashma is going to carefully choose a much smaller subcollection, and that's going to be the high-level idea, and this achieves nearly optimal parameters. To carefully choose those walks, it's a bit involved. You need some ideas based on the zigzag product. You're not going to cover those, but it's a beautiful result. But you are interested in the coding, right? You would like just to see what the coding direct sum looks like, right? And let's start with this setting that we have a base code of this bias and of this distance. You have this collection here of tuples, and then you're taking the direct sum, and you're achieving this distance for completeness. Okay, and what did the coding task looks like? We start from some pristine code word here. It gets corrupted to y tilde, showing the unique decoding ball. And if you think about it, this is going to give us a CSP, right? The corrupted code word here is defining the right-hand side of a bunch of XOR equations here. So it says you're given this corrupted word, and you'd like to find a Z in the base code such that when you compute the parities here, they agree as much as possible with the given y tildes on the right. Okay, so you're looking at this like K XOR. So more precisely, you have these. You're trying to find the Z in the base code such that when you compute the XOR, it agrees as much as possible. Okay, it looks like XOR, but it's not exactly XOR, not far. And if you'd like to understand this as a general CSP, right? Our assumptions are such that we know that the optimal value of this CSP is at least bounded by below by these, right? Because this solution achieves at least this value, right? It cannot, by our unique decoding assumption, cannot differ too much, right? And then this gives us a lower bound. Okay, but now we are in this regime that we relax. We ignore that. We don't want to restrict our attention to code words on the base level. We are focusing on an arbitrary one. Let's say that we can compute an optional one, an optional Z tilde for this CSP. And by what we said before, the CSP achieves at least this value, which means that when you take the direct sum here of this code word, the difference between the right-hand side is small, right? Because the CSP is quite satisfiable. And now applying triangle inequality, if you want to bound the distance between the unknown code word, this is y star, and our approximate solution, we can use triangle inequality. This part is by assumption because you're doing unique decoding and at most half of the distance. And this by the quality of the lower bound that you have in the optimal value of the SSP, this is also at most half of the distance. So overall, we know that our approximate solution and the solution that you'd like to retrieve, they have non-trivial bias, right? They are close to each other, which implies that when you compute their biases, you have a non-trivial bias. And now you can use the paired sampling property, right? If the paired sampling property is strong enough, then either the solution or its complement is going to lie in the unique decoding ball of the Z star, and you will be done. If you want to plug concrete parameters, those should suffice. And what is the moral here? The moral is that it's enough to find any solution here. So you find a Z tilde belonging to F2 to the N, rather than some guy in some code word in C0. And once you have this very good solution, what you can do, you can use the unique decoder to correct either this guy or its complement to choose this star. That's the moral. But with your solving, you claim that you can solve a KCSP, right? And why can you solve at least in our case? It should be hard even to approximate those guys, and you're only going to approximate. And it's going to be possible here because we are dealing with expanding structures. Okay? And the kind of result that is available is they are based on the sum of squares, semi-definite programming hierarchy. And for a collection of tuples, there is this new notion of introduced here and here, called sigma splittable. So it's a notion of expansion. And if you're sufficiently expanding, according to this, then you can get this additive approximation. The running time is polynomial, but not the best one. And this builds on our previous work and also on Barak-Rogat and Sawyer. And to define splittability, we are going to take this collection and you're going to look at sections of these. So suppose that we restrict the tuples to an interval AB. So we have this AB, and for every tuple in the collection, you just take this subinterval. And splittability is going to be a recursive notion. So we will start with this collection. And if it has size 1, you're done. But if not, it's larger, then you're going to break this K tuple into 2 parts, the first half and the second half. And you're going to define this operator, and you'd like this operator to be expanding. So this operator is as follows. When you take the first half of the second half, if they compose to a tuple in your collection, you're going to put a 1, otherwise you put a 0 there. And when you normalize the operator and look at the second similar value, is at most sigma, you declare that it's expanding, it's good, and then you recurse. So you want this collection to be sigma splittable, and this other one to be sigma splittable as well. And splittability was quite important for us because it was the property that allows us to solve those K XOR instances. It was the special structure that, and for a collection of all walks on a gamma, on a sigma two-sided spectral expander, it's sigma splittable. But what about the code parameters, right? We need to put things together. So we have the CSP machinery, we have paired sampling on the other side. We need to combine both and do unique decoding. So what we got in this previous work was nowhere near the state of the art. So we have distance half minus epsilon and quasi-polynomial rate. The decoding time was polynomial, but yeah. And not only did unique decoding, but we did least decoding. Somehow, while solving those SDPs, we can think that we had some sort of entropic potential, that it was making the SDP solution richer, and then we could do least decoding. It's as if we leverage unique decoding to least decoding. We need to work for that. It's not immediate, but it's a bit generic. And it was independently used by those authors here. And again, the parameters are not great for least decoding. The rates is still quasi-polynomial, and this is very far from the state of the art. But the decoding is polynomial time. And what do we have at this point? We have a Tashmas construction that's very refined, near optional, and you have this machinery or decoding machinery which is very parameter hungry. So something needs to happen for the decoding of Tashma to occur with near optional parameters. And I will only be able to discuss those ideas at a very high level and what they are. So the first thing that we need to do is to modify Tashma's construction slightly to obtain splittability. Because now with splittability, we can apply our machinery, right? And recomputing the parameters of unique decoding with the splittable version of Tashma, we have a new unique decoding algorithm. And you can ask, what are the parameters? How they raise? And before we say something about that, let's just remember, digress a little bit about SOS. So the SOS is essentially a generalization of linear programming. It's a hierarchy of SDP. It's great for solving CSPs. It's very powerful, but it's a bit slow, right? You pay a lot for, if you have the levels in this hierarchy, you pay this factor. And that's partially the reason why our running times are polynomial, but not the polynomials that one would like. Okay. So in terms of techniques, we are going to apply this SOS hammer, the unique decoding to our unique decoding problem. Unfortunately, as in the previous case, we will fail miserably. It's not good. It's still yielding quasi-polynomial rate. Okay. Now we are going to enhance, we are going to take, okay, we also have a least decoding machinery, right? And the observations that you're going to do least decoding to perform unique decoding, right? And this was considered in some previous works of Guruswamy and Indic. This is like killing a fly with a bazooka, but we are going to achieve better parameters by doing so. Okay, so now we try it again. This time around, some parameters are better. Cannot precisely say which ones, but some of them are better. Okay, you need to bring a new ingredient, and this ingredient is going to be a recursion. So, and we call it this code cascading. So, what is going to be? You're going to take advantage of the recursive structure in Tashma's walks. So, in short, you can see that if you take a walk in which every vertex is a walk itself, then you're going to end up with a larger walk. Now, if you take a walk over larger walks, then you're going to have an even larger walk. And if you take walks over even larger walks, you're going to have an even larger walk, and so on, right? And this kind of recursive nature would allow us to define a sequence of code. So instead of going in one shot from the base code all the way to a code of bias epsilon, we are going to form incrementally. You do direct sum and form code C1, direct sum, form code C2, and then so on and so forth. The advantage here now is that when you're going to do the decoding test doesn't need to start from here, decoding all the way back here. So it's going to be in between levels. So if you want to decode a guy here, it's going to invoke the unique decoder here. And it's only a nearby interaction. And the parameters are going to be much weaker in this. So this code cascading allows you to drastically reduce the parameter requirements. And Guruswamy and Indic in the previous work, they also had some form of cascading. They don't call it this way, but it's for the direct product. It's quite different than ours, but they have some construction of this sort. And combining the least decoding via SOS, this recursion, we can obtain unique decoding. So we decode Tashma's codes with near optimal rate. That's all. Thank you very much for your attention.